Hello students, we have studied the Cauchy's first theorem on limits yesterday, okay, which states that whenever limit of an is L, limit an is L, limit a1 plus a2 plus an divided by n is also L, using which we have examples here. Show that limit 1 by n into 1 plus 2 power 1 by 2, 3 power 1 by 3, n power 1 by n. Actually 1 power 1 by n, 1 by 1 agutte. You want to show this limit value equal to 1 by using Cauchy's first theorem on limits. Let it take an equal to n power 1 by n. What is limit an? It is limit of n through n. This already you have studied. Limit n through n is 1 from your knowledge. Okay, so take an equal to n power 1 by n. So limit an is going to be 1. Now apply Cauchy's first theorem on limits. That is limit of a1 plus a2 plus etc. an by n. By the theorem, this limit value is also same. Idu L idre idu L irutte. Idu 1 adre idu kuda 1 agutte. Okay. Here what is 1 by n element alla? 1 by n is here. What is a1? 1 power 1 by n. a2. a2 is 2 power 1 by 2. a3. 3 power 1 by 3 etc. etc. an is n power 1 by n. That's equal to 1. Okay. Small problem but important. Even here also the second question. You multiply and divide by n here. It is 1 by root n square plus 1. 1 by root n square plus 2, etc. 1 by root n square plus n. What you need to watch here is that only second term is changing here. Root na odage second term change agutte. Idu 1 aitu, idu 2 aitu, 3 aitu, illi n aitu. So changing variation agodu only in the second term. Okay. If you multiply and divide by n, you want to show this. Idu Cauchy first theorem on limits alli sigutte namage actually. Okay. We are multiplying by n and dividing by n. Take an equal to n by root n square plus n. Please note that here only the second term is changing. This is changing. Actually the index r anta baribodu. R varying from 1 to n. Okay. What is limit an? You know how to take the limit. Divide the numerator and denominator by n. If you divide by n, it will be 1 I2. Root n square. If you take it out, the n cancel agi istu ulitu. 1 by n is tending to 0 as n tends to infinity. Right? So, the limit value is 1. By Cauchy's first theorem on limits, limit of a1 plus a2 plus up to an by n is also 1. The 1 by n is 1 by n. 1 by n is here. a1 is you are changing only the second term. n by root of n square plus 1. a2, n by root of n square plus 2, etc. etc. an is this. This is going to be 1. But even the n common is there. This n and this n you can cancel. Therefore, given limit is also 1. So these are two simple problems, but important. You are likely to get one question in the exam here. Okay. So this is about Cauchy's first theorem on limits. Now, we will proceed for today's topic. Right? That is to study today's topic, you should be knowing what is supremum. Supremum, what is infimum. You have studied limit superior. Right? Limit superior you have studied. Limit super. Limit inferior you have studied. But this is different. Limit superior andre a larger among all the limit points. Limit inferior andre smaller among all the limit points. So idu very concept adu. Supremum andre least upper bound adu. Least upper bound. Infimum means greatest lower bound. Greatest lower bound andre greater among all the lower bound. Least upper bound andre smallest among all the upper bounds. Okay. When do you say that sequence Sn is bounded above? A sequence is Sn is said to be bounded above by a number say m, bounded above by m or k, if every term of the sequence is less than or equal to k. If every term of the sequence is less than or equal to k, then sequence is bounded above. Okay, k is an upper bound. Any value to the right of k is also an upper bound. K plus 1 early, fraction early, anything. Any value greater than k is also an upper bound. Okay, for your sequence 1 by n, all the terms are between 0 and 1. Here 0 is a lower bound and 1 is an upper bound. Okay, any value to the right of 1 is also an upper bound. 1.5 is an upper bound, 1.1 is an upper bound, 2 is an upper bound, 2.1 is an upper bound, etc. etc. Among all the upper bound, which is the least one? Least is 1. This is called supremum or least upper bound, LUB. For the sequence 1 by n, the greatest lower bound is 0. Any value smaller than 0 is also a lower bound. You take minus half, minus 1, 1.1, anything. Any value smaller than 0 is also a lower bound. Among all the lower bounds, which is the largest, the greatest lower bound, that is 0. Greatest lower bound is called infimum. Least upper bound is called supremum. Right? So, supremum and infimum. You have an axiom called completeness axiom. Right? Completeness axiom. What do you mean by completeness axiom? You take any non-empty subset of real numbers. Say S is a non-empty subset of a real number, set of real numbers. Okay. Every non-empty subset of real numbers which is bounded above has a supremum, has a least upper bound. Right? Similarly, every non-empty subset of real numbers which is bounded below has a greatest lower bound, that is infimum. Infimum. Least upper bound is supremum. I repeat, completeness axiom is stated as every non-empty subset of real numbers which is bounded above has least upper bound. Every non-empty subset of real numbers which is bounded below has a greatest lower bound, that is supremum and infimum. This is completeness axiom. Next, I just added 2 more definitions here before the theorem. Monotonic sequence and monotonic sequences. Okay, monotonic sequence there are 2 types. One is monotonic increasing. Monotonic increasing, and upward arrow increasing. And monotonic decreasing sequences. Downward arrow decreasing decreasing sequence. A sequence Sn is said to be monotonically increasing. If every term is less than or equal to next term for all n. Sn less than or equal to Sn plus 1 for all n. Monotonically increasing sequence. Monotonically decreasing sequence Sn is greater than or equal to Sn plus 1. Right? For every n. First term is greater than second term. Second term greater than third term. Right? Etc. Monotonically decreasing monotonically increasing Sn less than or equal to Sn plus 1. Okay. A monotonic increasing sequence you can further define strict monotonic increasing. Strict monotonic increasing Sn is strictly less than Sn plus 1, equal to love. It is strict monotonic increasing. What is strict monotonic decreasing? As naturally you can think, Sn is greater than Sn plus 1 for all n. Strict monotonic decreasing, strict monotonic increasing. Equality tegre strict agade. Equality idre it is monotonically increasing or monotonically decreasing. Remove equality, strict monotonic increasing and strict monotonic decreasing. Having noted this, we come to a theorem that a necessary and sufficient condition for the convergence of a monotonic sequence is that it is bounded. ಈ necessary part ಯಾವುದು? Assume that sequence is monotonic. Let Sn be monotonic, the monotonic sequence. Sn be a monotonic sequence. Okay. And assume that it is convergent. A sequence is convergent. If and only if it is bounded. ಅಂದರೆ ಹೇಳಬೇಕು ನೀವು. See, whenever the sequence is convergent, it is bounded. We have already proved. Every convergent sequence is bounded. You are assuming that a monotonic sequence. Monotonic sequence ಅಂದರೆ it can be monotonically increasing or monotonically decreasing. Okay. Such a sequence is converging ಅಂತ ನೀವು assume ಮಾಡ್ತೀರಾ. Converging to L ಅಂತ. What do you want to prove? It is bounded. Convergence implies bounded. Already we have proved. The same proof is copied down here. ನೋಡಿ ಬೇಗ ಕ್ವಿಕ್ ಆಗಿ. Assuming that sequence Sn is converging to L, for given epsilon greater than 0, there exists a positive integer m for which mod Sn minus L is less than epsilon for all n greater than or equal to m. Okay. So this implies your Sn minus L lies between minus epsilon and plus epsilon. Adding L on either side, L minus epsilon less than Sn less than L ಆಗಬೇಕಿದು L plus epsilon. A ಅಲ್ಲ L. Okay. Sn lies between L minus epsilon and L plus epsilon. ಇದು ಕರೆಕ್ಷನ್ ಮಾಡಿ L ಇದೆ. You take small k as the minimum of, ನೋಡಿ ಇದು after mth term you are having here. Okay, first m minus 1 terms ಇಲ್ಲಿ ನೋಡಿ S1, S2, Sm minus 1. Okay, ಆಮೇಲೆ one more value is L minus epsilon. ಇದು Sn ಇಂದ ಚಿಕ್ಕದು. ಎಷ್ಟು ವ್ಯಾಲ್ಯೂಸಲ್ಲಿ ಯಾವುದು ಸ್ಮಾಲೆಸ್ಟ್ ಉಂಟು ಮಿನಿಮಮ್ ಉಂಟು ಕಾಲ್ ಇಟ್ ಎಸ್ ಸ್ಮಾಲ್ ಕೆ. ಸಿಮಿಲರ್ಲಿ ಈ ಫಸ್ಟ್ m minus 1 ವ್ಯಾಲ್ಯೂ ಹಿಯರ್, ಫಸ್ಟ್ m minus 1 ವ್ಯಾಲ್ಯೂ S1, S2, Sm minus 1. ಮತ್ತು ಇಲ್ಲಿ ಈ ಟರ್ಮಿನ ರೈಟಿಗೆ ಬರುವ ವ್ಯಾಲ್ಯೂ L ಪ್ಲಸ್ ಆಪ್ಸಿಲಾನ್. ಇದು ಇಷ್ಟು ವ್ಯಾಲ್ಯೂಸಲ್ಲಿ ಲಾರ್ಜರ್ ಯಾವುದುಂಟು, ಮ್ಯಾಕ್ಸಿಮಮ್ ಯಾವುದುಂಟು, ಟೇಕ್ ಇಟ್ ಆಸ್ ಕ್ಯಾಪಿಟಲ್ ಕೆ. ಬೈ ದೆನ್ every term of the sequence Sn lies between small k and upper k. It is bounded above and bounded below, and hence it is bounded. So every convergent sequence is bounded. It is already proved. The same proof is adopted here. Okay. There is the necessary part. Right? Sequence to be bounded is necessary for the convergence. Clear alla? Boundedness is necessary for convergence. Necessary ಅಂದರೆ ಹಾಗೆ. ಈಗ ಸಫಿಷಿಯಂಟ್ ಪ್ರೂವ್ ಮಾಡಬೇಕು. ಸಫಿಷಿಯಂಟ್ ಅಂದರೆ you assume that sequence is monotonic sequence which is bounded. Monotonic sequence which is bounded. We want to prove that sequence is convergent. This is condition. Monotonic and boundedness is required for convergence. What is sufficient? If the sequence is monotonically increasing and it is bounded, that is sufficient for convergence. Clear ಅಲ್ಲ? ಈಗ ಮೊನೋಟೋನಿಕ್ ಅಂದರೆ ಎರಡು ಕೇಸ್ ಬರುತ್ತೆ, ಮೊನೋಟೋನಿಕ್ ಇನ್ಕ್ರೀಸಿಂಗ್, ಮೊನೋಟೋನಿಕ್ ಡಿಕ್ರೀಸಿಂಗ್. ಲೆಟ್ ಮಿ ಕನ್ಸಿಡರ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಕೇಸ್ ಆ್ಯಂಡ್ ಬೌಂಡೆಡ್ ಅಬೋವ್ ಕೇಸ್. ಮೊನೋಟೋನಿಕಲಿ ಇನ್ಕ್ರೀಸಿಂಗ್ ಆ್ಯಂಡ್ ಬೌಂಡೆಡ್ ಅಬೋವ್. ಓಕೆ, ನೀವು ಮೊನೋಟೋನಿಕ್ ಅಂತ ಹೇಳುವಾಗ ಮೊನೋಟೋನಿಕಲ್ಲಿ ಯು ಹ್ಯಾವ್ ಟೂ ಕೇಸಸ್, ಮೊನೋಟೋನಿಕ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಆ್ಯಂಡ್ ಮೊನೋಟೋನಿಕ್ ಡಿಕ್ರೀಸಿಂಗ್. ಬೌಂಡೆಡಲ್ಲಿ ಎರಡು ಕೇಸ್, ಬೌಂಡೆಡ್ ಅಬೋವ್ ಆ್ಯಂಡ್ ಬೌಂಡೆಡ್ ಬಿಲೋ. We will take the first case, monotonic increasing and bounded above. Increasing ಅಂದರೆ ರೈಟಿಗೆ ಹೋಗ್ತೇವೆ ನಾವು, ರೈಟಿಗೆ ಹೋಗುವಾಗ ಅಪ್ಪರ್ ಬೌಂಡ್ ಬೇಕಲ್ಲ. ಮೊನೋಟೋನಿಕ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಆ್ಯಂಡ್ ಬೌಂಡೆಡ್ ಅಬೋವ್. ಸೀಕ್ವೆನ್ಸ್ Sn is monotonically increasing and bounded above. Proof is similar for monotonic decreasing sequence which is bounded below. ಈ ಪ್ರೂಫ್ ನೀವು ಸಪ್ಲೈ ಮಾಡೋದು ಬೇಡ, ಸಿಮಿಲರ್ ಅಂತ ಬರೆದ್ರೆ ಸಾಕು. ಓಕೆ, so on assuming that sequence is monotonically increasing and bounded above, we will prove that the sequence Sn is convergent. Convergent ಗೆ ಏನು ಬೇಕು? Convergence ಗೆ you want mod Sn minus L less than epsilon. Okay, convergence is required for you. We will prove that sequence is convergent. Okay. Let S be the range of the sequence. Right? When you say that sequence is bounded, its range is nothing but members of the sequence. The terms of the sequence is the range. When you say that sequence is bounded, range is bounded. Range set on S and the range is bounded. Let S be the range of the sequence which is clearly bounded above. Because sequence is bounded above, the range is bounded above. You have studied completeness axiom. Just now you have studied completeness axiom. What is it? A non-empty subset of real numbers which is bounded above has the least upper bound or supremum. So by the completeness axiom, the set S has the least upper bound or supremum. It's also called supremum. Least upper bound or supremum. Right? We call this least upper bound as M. Fine? Because S is the range of the sequence which is bounded above by the completeness axiom, completeness property. S has the least upper bound, we call it as M. Let us show that our sequence is converging to M. Job is very simple. Convergence actually you want to prove that you want to prove this nodi. Mod Sn minus M is less than epsilon for all n greater than or equal to M. This is what actually you want to prove. Okay. You take epsilon greater than 0. Let epsilon greater than 0 be given. Okay. M minus epsilon is a number smaller than M. ನಮ್ಮ ಕ್ಲೇಮ್ ಏನಂದರೆ ಬೈ ಚೂಸಿಂಗ್ ಸೂಟೇಬಲ್ ಆಪ್ಸಿಲಾನ್ ಸೈಜ್ ಉಂಟಲ್ಲ ಅದನ್ನು ವೇರಿ ಮಾಡೋದ್ರ ಮೂಲಕ ಇಫ್ ನೀಡೆಡ್ ಯು ಹ್ಯಾವ್ ಟು ವೇರಿ ಇಟ್ ಯು ಆರ್ ಏಬಲ್ ಟು ಫೈಂಡ್ ಎ ಟರ್ಮ್ ಆಫ್ ದ ಸೀಕ್ವೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದೀಸ್ ಟು. ಫೈನ್, ಯು ಆರ್ ಏಬಲ್ ಟು ಫೈಂಡ್ ಸೇ Sn, ಒನ್ ಆಫ್ ದ ಟರ್ಮ್ ಆಫ್ ದ ಸೀಕ್ವೆನ್ಸ್ Sn. ಈ ಸೀಕ್ವೆನ್ಸಿನ ಒಂದು ಟರ್ಮನ್ನು ಎಮ್ ಮೈನಸ್ ಆಪ್ಸಿಲಾನ್ ಮತ್ತು ಎಮ್ಮಿನ ಮಧ್ಯೆ ತಂದು ಕೂತ್ಕೊಳಿಸ್ಬೋದು. ರೈಟ್? Though epsilon is very very small, still you can accommodate a term of the sequence between m minus epsilon and m. How? If it is not possible to do it, you just vary epsilon ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಕಡಿಮೆ ಮಾಡಿ 0.001 ಉಂಟು, ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ವ್ಯಾಲ್ಯೂ ತಗೊಳ್ಳಿ, ಆಗ ಇಲ್ಲಿ ಗ್ಯಾಪ್ ಬರುತ್ತೆ. ಆ ಗ್ಯಾಪಲ್ಲಿ ಒಂದು ಟರ್ಮ್ ತಂದು ಹಾಕ್ಬೋದು. Since m minus epsilon is a number less than m, the least upper bound, there exists at least one member Sm which is greater than m minus epsilon. ಈ m ಮತ್ತು m minus epsilon ಮಧ್ಯೆ ಒಂದು ಟರ್ಮ್ ತಂದು ಹಾಕಲಿಕ್ಕೆ ಆಗುತ್ತೆ. Sm is greater than this. ಓಕೆ. ಸೀಕ್ವೆನ್ಸ್ ಇಸ್ ಮೊನೋಟೋನಿಕಲಿ ಇನ್ಕ್ರೀಸಿಂಗ್ ಅಂತ ನಾವು ಎಸ್ಯೂಮ್ ಮಾಡಿದ್ದೀವಿ. ನೋಡಿ, ವೆನ್ ಎವರ್ n is greater than or equal to m, Sn is greater than or equal to Sm. ಮೊನೋಟೋನಿಕ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಅಂದರೆ ಆಗಲ್ಲ. ರೈಟ್? S1 less than or equal to S2. ಇಲ್ಲಿ 1 ಮತ್ತು 2 ನೋಡಿ, 1 less than or equal to 2. S1 is less than or equal to S2. ಮೊನೋಟೋನಿಕಲಿ ಇನ್ಕ್ರೀಸಿಂಗ್. ಇಲ್ಲಿ n is greater than or equal to m ಅಂದರೆ ಹೀಗೆ ಬರುತ್ತೆ ನೋಡಿ, m less than or equal to n. ಆಗ Sm is less than or equal to Sn. Because it is monotonically increasing. Sn is greater than or equal to Sm. Because n is larger. Sm is greater than m minus epsilon. ಇಲ್ಲಿ ಬಂತು. ಓಕೆ. ನೆಕ್ಸ್ಟ್, ಸೊ ಮೊನೋಟೋನಿಕ್ ಇನ್ಕ್ರೀಸಿಂಗ್ ಇಲ್ಲಿ ಯೂಸ್ ಮಾಡಿ ಆಯಿತು. ನೆಕ್ಸ್ಟ್, ಯು ಹ್ಯಾವ್ ಸೆಟ್ ದ್ಯಾಟ್ ದ ಸೆಟ್ ಎಸ್ ಹ್ಯಾಸ್ ದ ಲೀಸ್ಟ್ ಅಪ್ಪರ್ ಬೌಂಡ್ ಎಮ್ ಅಂತ ಹೇಳಿದ್ದೇವೆ. ಸೊ ಲೀಸ್ಟ್ ಅಪ್ಪರ್ ಬೌಂಡ್ ಆಫ್ ದ ಸೀಕ್ವೆನ್ಸ್ ಇಸ್ ಎಮ್. ವಾಟ್ ಯು ಮೀನ್ ಬೈ ಸೇಯಿಂಗ್ ದಟ್ ಎಮ್ ಈಸ್ ದ ಲೀಸ್ಟ್ ಅಪ್ಪರ್ ಬೌಂಡ್? ಫಸ್ಟ್ ಆಫ್ ಆಲ್, it should be an upper bound. And it is least among all the upper bounds. Since m is the least upper bound, it should be an upper bound first of all. Upper bound ಅಂದರೆ ಏನು? Every term of the sequence is less than or equal to m. Clear ಅಲ್ಲ? For every n greater than or equal to m, this happens. And m is obviously less than m plus epsilon, m plus something. Okay, fine. Call this as 2. Because m is the least upper bound, it is an upper bound first of all. Upper bound means every term of the sequence should be less than or equal to m, and m is obviously less than m plus epsilon. This inequality you are getting. So from inequality 1 and inequality 2, we conclude our work. Start with m minus epsilon. M minus epsilon is strictly less than Sn. Sn is strictly less than m plus epsilon. So your Sn lies between m minus epsilon and m plus epsilon. Adding an m on either side, add m. ಏನು ಸಿಗುತ್ತೆ? ಇಲ್ಲಿ m ಕ್ಯಾನ್ಸಲ್ ಆಯಿತು, ರೈಟ್? ಇಲ್ಲಿ m ಕರೆಕ್ಷನ್, you are subtracting m, not adding. subtracting m, ಇಲ್ಲಿ m ಕ್ಯಾನ್ಸಲ್ ಆಯಿತು, ಇಲ್ಲಿ m ಸಬ್ಟ್ರಾಕ್ಟ್ ಆಯಿತು, ಇಲ್ಲಿ m ಕ್ಯಾನ್ಸಲ್ ಆಯಿತು. you are subtracting, adding minus m or subtracting m or adding minus m. ಆಗ ಇಲ್ಲಿ ಮೈನಸ್ m ಪ್ಲಸ್ m ಕ್ಯಾನ್ಸಲ್ ಆಯಿತು, ಮೈನಸ್ m ಪ್ಲಸ್ m ಕ್ಯಾನ್ಸಲ್ ಆಯಿತು, ಇದು Sn minus m ಆಯಿತು. So your Sn minus m lies between minus epsilon plus epsilon, to mean that mod Sn minus m less than epsilon for all n greater than or equal to m. This is nothing but saying that sequence Sn is converging to m. Okay, sequence Sn converges to m. What is m? M is the least upper bound or supremum. So sequence converges to its least upper bound or supremum. That's what you wanted to prove. Okay, the sequence converges to the least upper bound or supremum. Fine. So what is the theorem? A necessary and sufficient condition for the convergence of a monotonic sequence is that it is bounded. If you take a monotonic sequence Sn, the convergence implies and implied by boundedness. Means convergence implies boundedness, and boundedness implies convergence. So you are assuming convergence first, proving boundedness. Assuming boundedness and then proving convergence. Then proving the convergence. So in this process we are using completeness action. Every non-empty subset of real numbers which is bounded above has a least upper bound or supremum, and every non-empty subset of real numbers which is bounded below has a greatest lower bound. Greatest lower bound case we are not discussing here, so I have not said much about it. The least upper bound is here. So we are proving that our sequence is converging to the least upper bound, that is m, for which this simple argument we are having. Please study that again. I am sure that you are going to understand it. Okay. If you have some doubts, please text. It will be attended or explained to you. Fine. We are almost coming to the end of the unit. Maybe within a couple of sessions we are completing the unit, and your cooperation is appreciated. And if any doubts are there, please clarify. Don't hesitate. Plenty of time is there before you. All that required is you have to utilize your time very, very effectively, so that your studies are not disturbed under any circumstance in the world. Thank you very much. We'll meet again in the next session. If possible, today's video I have not yet sent to you. I'll just try to do that because I have some work in the college. I could not attend this, please wait. If possible, I'll send it today itself, otherwise tomorrow and day after tomorrow. Thank you.